Classification of matter. Well, first of all, we need to define matter. Matter is anything that occupies space and has mass. So, this little weather station occupies space, has mass. This is matter. Paper towels, matter. Your body is made of matter. What about the air in this room? Does air occupy space? Yeah. If you put air into a balloon or a bike tire, you can see, you can experience, observe that air can occupy space. Does air have mass? Well, that's not immediately obvious, but yes, air has mass. Air is matter. How about anger? Is anger matter? No. Anger matters, but it isn't matter, right? It's an emotion. It doesn't have mass. It doesn't take up space. We also use the word substance a lot. And when a scientist says substance, we mean a specific instance of matter. There are so many different kinds of matter that we use substance. So, a paper towel could be a substance. Paper is a substance. Soapy water could be a substance. We use that so that we don't have to specify, okay, this is an ion, that's an atom, this is a molecule, this is a homogeneous mixture. It's just kind of a generic word. So, just like with Lego blocks, we need some way to describe them or organize them. We've tried this a few times. You could organize Lego blocks in many different ways. You could sort them by color. We'll put all the red ones over here and all the blue ones over there so that you could find them when you need a particular piece. You could sort them by size. Okay, here's all the 2x4 bricks, and there's all the 2x2 bricks, etc. You could sort them by what set they came from. You could sort them by how big they are, big ones and small ones, all kinds of different ways. We're going to talk about two main classification methods for matter. That's my friend, the freight train. Is he done? I think he's done. Okay, so we can classify matter by its state or by its composition. Its state, we mean its physical form. And the composition means what are the components that make it up. Let's look at the state first. So there are three major states of matter: solid, liquid, and gas. There are a couple others, but they're very unusual, and we're not going to talk about them in this class. So let's think about water, because in everyday life we experience water in all three states. When it's a solid, we call it ice. Ice is frozen water, right? It's solid. We call liquid water just water. And then water in the gas state has lots of different names. You might call it steam or humidity or mist, or a cloud is sort of like, it's not technically in the gas state, but kind of. We also know that if you take a solid like ice and you heat it up, you can increase the temperature, you can cause it to melt into a liquid. And if you heat the liquid, you can make it go into the gas state. It's important to understand at the particle level what is different about solids, liquids, and gases. And this illustration helps with that. Here we're looking at something made of these little green balls. Now, I don't know what those are. Just little spheres. So here the little atoms are all very close to each other, and they are fixed in space. They're not moving. Students also have three states: solid, liquid, and gas. Right now, the students in this class are in the solid state because you're all stationary, right? The person sitting behind you or next to you has been behind or next to you for several minutes now. We're not moving relative to each other. Are all of you perfectly still? I hope not. I would like at least for you to be breathing, okay? Even if you're asleep, please continue to breathe, okay? You are moving. Some of you fidget more than others. That's okay. And by the way, if you're one of those people that just can't sit still and you want to pace in the back of the room, go at it. It won't bother me at all. So students in lecture are in the solid state. In lab, we're going to be getting up and we're going to be moving. you'll have to go over here and get some chemicals, and you'll have to walk over there and go to the balance, and we're moving around. That's what liquids do. The particles are still very close to each other, but now they're moving relative to each other. The gas state for students is like when class is over and you diffuse out the doorway and you just go off in your separate ways. And some of you go very far away and some of you don't go very far away, but there's a good chance that you might not see the other students in this class until you come back to the solid state again on Thursday for lecture. Okay? So I'm going to go through these slides pretty quickly because I basically already said all this stuff. Solid matter. Actually, I think I'm going to do some underlining. So the particles are close to each other in fixed locations. That's the key thing of solids. The particles, the atoms, molecules, they do vibrate, but they don't move relative to each other. And as a result, a solid has a fixed volume and a rigid shape. Solids do not change their shape. They do not change their volume when you move them from one container to another. We can divide solids into two broad categories as well, crystalline solids or amorphous solids. In a crystalline solid, we have patterns. So this diamond is a crystalline solid. The carbon atoms in here are arranged in a very specific pattern, and that pattern extends in 3 dimensions. It's a crystalline solid. Another example of a crystalline solid is table salt. If you go home and you look at the little tiny grains of salt, they're all little tiny cubes. And that's not because Morton spent a lot of money making them into little cubes. That's because sodium chloride naturally arranges itself that way. The other category is amorphous. This prefix A means without. So amorphous means without shape. There's no long-range order. An example of that would be glass or plastic. The particles are not arranged in a nice, orderly way like they are in a crystalline solid. In liquids, the particles are also close like they are in solids. So they are close together. Sometimes we say that they're touchingly close. But now they can move relative to each other. So sliding around. As a result, liquids have fixed volume because the particles always stay close to each other, but they do not have a fixed shape. So you take a cup of water, and it's 1 cup, and you pour it into a bowl. It's still 1 cup in volume, but its shape has changed. You could go from a tall, skinny bowl into like a cookie sheet, and it'll spread out. The volume doesn't change, but the shape does. So they take on the shape of their containers. In gases, there's lots of space. Gas particles are not touchingly close. A lot of space between the particles. They also are free to move relative to each other. These qualities make gases compressible. So here we have an illustration of a piston. So we've got a solid in here, and we're pushing down on it with this piston, and you can push all you want. These molecules are already touching each other. You can't squish them together anymore. You can't compress them. In a gas, there's a lot of space between them, and so you can push the gas particles closer together. If you continue to press on a gas, you'll turn it into a liquid and eventually into a solid. So gases are compressible. And what really should be on this slide, which is not, is that gases have variable shape, and volume. So we're familiar with liquids taking on the shape of their container. Gases will take on the shape of the container. They'll also take on the volume of the container. It's a little bit like a homework assignment. It will expand to fill the amount of time you have available, right? A gas will expand to fill whatever container it's in. So any questions about classifying by state? Okay, so classifying by composition. This illustration kind of gives us an overview. So we can divide matter into pure substances or mixtures. And the difference between these is, does it have a variable composition, or is the composition always the same? If the composition is always the same, then it's a pure substance. Two categories of pure substances are elements and compounds. And the factor here is, can you separate it into simpler things? If you cannot, you have an element. If you can separate it, then you've got a compound. Over here at the mixtures, two categories of mixtures, heterogeneous and homogeneous. Hetero is a prefix that means different or opposite, and homo is a prefix that means the same. So a homogeneous mixture is uniform throughout. A heterogeneous mixture has two or more distinct parts to it. The example here is wet sand. You can see there's the liquid water and there's the solid sand. It's not all the same. If you look at tea with sugar in it, the sugar dissolves and mixes thoroughly in the tea, and it's the same throughout. It's uniform. So pure substance made up of only one component, and its composition is invariant. Another way to think of this is, if you go down and look at the particle level for a pure substance, all the particles, whether they're atoms or molecules, are going to be the same. So we could have water molecules. That gray's not dark enough. I used a different example yesterday, and I realized halfway through that I didn't like it very much, so I'm using this one today. So if you look at water, and you were able to go down and look at the individual pieces, you would see that all the water molecules are the same. There's lots and lots of water molecules, but they're all the same. One red, two white. One oxygen, two hydrogen. That's a pure substance. You could also have a pure substance that's maybe, let's do this. You might have like aluminum. Okay, and so you've got aluminum atoms in aluminum foil, and all the individual particles are the same. That's a pure substance. In a mixture, you don't have all the particles being the same. So water is composed of two different elements, oxygen and hydrogen. You could have a mixture of hydrogen and oxygen. There's the hydrogen, and here's the oxygen. Okay, so here again we have hydrogen and oxygen, but now there's two different kinds of particles. That means it's a mixture. Because I could change. Right now I have two oxygen particles and two hydrogen particles. But I could throw in another oxygen particle. The composition has changed. It's not 50-50 anymore. Now I've got more oxygen. You can change the composition. With something like this, you can't change the composition. If I throw in more aluminum atoms, it's still just all aluminum atoms. They're all the same. I can't change the ratio of oxygen to hydrogen here because each of these molecules is the same. If I add more particles, they're going to be the same kind of particle, and it's still going to be two hydrogens for every one oxygen. Whoops. Any questions? Those pure substances fall into two categories, elements and compounds. And it has to do with, can you break it down into something simpler? I need to learn how to copy and paste on this thing. Right now is not the time to learn how to do that. So I'll just draw them again. So here's my water that I was using as an example. Here's my aluminum foil. Can I take this aluminum foil and break it into two simpler things? I can't. I could cut it in half, but Both halves are still aluminum now. And I can't break atoms. Just like, when you're playing with Legos, you can't take a 2x4 brick and cut it in half with your hands and make two 2x2 bricks. You just can't do it. Atoms do not get destroyed in a chemical reaction, and so we can't just cut these in half. But what about the water? Could I separate the hydrogen from the oxygen? Yes, I can. And it's actually as simple as passing some electric current through the water. You could try that at home with tap water and a 9-volt battery. Drop a 9-volt battery into a glass of tap water and watch it for a minute or two, and you'll see little tiny bubbles forming at the terminals. The bubbles at one terminal are oxygen molecules, and the bubbles at the other terminal are hydrogen atoms. You're decomposing the water. You're breaking the water down into simpler substances. So water is a compound. Aluminum is an element. Any questions? So elements cannot be broken down into simpler substances. They're the basic building blocks. Compounds have 2 or more elements in them. The thing is that what that distinguishes them from a mixture is that they are combined in fixed proportions. And if we look at the individual molecules, all the molecules are the same. So again, just like I said, we don't often find individual atoms in nature. We don't often find elements in nature. Usually things are combined into compounds. Well, what about those mixtures? Heterogeneous versus homogeneous. Depends on how uniformly the things mix. So in a heterogeneous mixture, we have a difference in composition from one part to another. An example would be a salt and sand mixture. Take a handful of sand, a handful of salt, throw them together in a bowl, mix them up. Look at it. You can still see, that's a salt crystal and that's a grain of sand. There's 2 distinct parts. Or like macaroni and cheese. There's the cheese sauce and there's the macaroni. You can see the lumps in the macaroni and cheese. It's a heterogeneous mixture. Could you put more cheese sauce on it? Sure. The salt and sand mixture, you could throw more salt in and it's still a mixture, right? It's not a compound. But it's heterogeneous because it doesn't mix thoroughly. You could look and say, okay, well, this part's more salty and that's more sandy. This part has macaroni in it and that's just the cheese. Homogeneous means that it mixes thoroughly. And homogeneous mixtures could sometimes be mistaken for compounds because you look at it and you're like, oh, it's all the same. It looks like one thing. Sweet tea. You put the sugar into the tea and it seems like the sugar disappears, right? You can't see it anymore. And if you taste different parts of the tea, it all tastes the same. It's mixed uniformly, and so that's a homogeneous mixture. Mixtures can be separated. And separating things is something that has a lot of practical use. How do you separate stuff? Well, you have to find out what makes it different. Say I've got spaghetti and I've got the water it's cooking in and I want to separate them from each other. I'm going to take advantage of the differences between them. One's a solid, one's a liquid. How do we normally separate spaghetti from the water it's boiling in? A strainer or a colander, basically a bowl with holes, right? You pour the whole pan of stuff into the strainer, and the water, being a liquid, goes through the holes. The spaghetti can't go through the holes. And so we're taking advantage of physical differences. A mixture of sand and water can be separated by decanting it. I'm going to draw you a bad picture. Okay, so there's my beaker, and it's full of water, and it's got sand particles. It's got sand. And you could stir it up, but when you stop stirring, the sand is going to fall to the bottom. How do you separate it? Well, the strainer wouldn't work here because the sand is small enough it can go through the holes. One way, it sounds all fancy, is called decanting. And all that means is that we're going to let the sand settle to the bottom, and then we're slowly going to pour the water off the top, so we can separate the water from the sand. That's a separation method. What if you have a homogeneous mixture of liquids? Say alcohol and water. They mix together. And what if you need to separate the alcohol from the water? How could you do that? Distillation. So you put your homogeneous mixture of liquids in here and you heat it up. The more volatile liquid, the liquid with the lower boiling point, will boil first and go into the gas state. Now we want to keep that liquid. We don't want it to just go away. So we've got this enclosed here, and it goes into the gas and it's trying to escape, and so it comes through this condenser. This has a double wall, so the gas is on the inside, and then in that space we're running cold water to cool that gas. I don't know why the screen keeps flickering like that. Cooling the gas, and it will condense. That's why it's called a condenser. So the alcohol will condense, and then it'll drip out the bottom. I didn't do that. It'll drip out the bottom, and we can collect it over here. The water stays behind. So we're separating the two liquids based on a difference in their boiling points. That's called distillation. Another way is called filtration. This is the basis of most coffee makers, is filtration. So if you have an insoluble solid mixed with a liquid, like coffee grounds in hot water, you can filter them. So we talk about a coffee filter, right? So filter paper has pores that allow the liquid to go through, but those pores are small enough that the coffee grounds, even if it's Turkish grind, I prefer the passenger trains. They sound so polite in comparison. They go toot, toot as they go by. And the freight trains, oh my goodness. Okay. It's the equivalent of seeing squirrels. So the coffee grounds can't go through, but the liquid can. And so we can separate the liquid from the solid. Filtration.